Hey everyone, we're back to solve some more problems in two-dimensional kinematics. This time we're going to do a problem in fully projectile motion, and we're going to do a little bit complicated one. We're going to do projectile motion where the height where you start is not the same as the height where you end. And the reason I'm going to do it this way is because problems like this encode the type of problem where they start and end at the same height as part of the analysis. And it's also a problem which is useful for illustrating what we mean when we say it's useful to solve the kinematic equations in phases. Okay, so the problem that we're going to look at is one that we've talked about in class several times, the so-called Megawoosh problem. You may remember this video of a guy sliding down the hill on a water slide and flying across the landscape and landing in a swimming pool. So let's imagine that I do this for the sake of your physics education. It actually looks pretty fun to me. And I'm only going to do this if you can accurately compute where to put the pool of water so I don't hurt myself doing this demo for you. So the initial speed when I leave the ramp from the water slide is 14 meters per second, and it's at an angle 40 degrees to the horizontal. That is, it's 40 degrees above the horizontal, and the ramp itself is 6 meters above the horizontal ground. And I want to know at what distance x from the foot of the ramp should you put the pool of water so that I don't die a horrible death doing this demo for you. Okay, so that's the problem. So the first thing I do with all physics problems, as you know, is I draw a diagram. And in this case, I'm going to draw a pretty large diagram so that we can go back and refer to it several times. Everything's based on the horizontal direction here. Okay, I'm going to label plus x to the right there. And I'm going to have the ramp, the foot of the ramp where I take off, at x equal to 0. So the ramp is something that goes off to the side here. Okay, let me color it in so we know it's not part of the problem. Okay, so I come off the ramp initially at some angle with some initial speed that I'm told is, what was the speed? 14 meters per second. Okay, and I'm also told that the angle that that velocity vector makes is 40 degrees to the horizontal. Okay, now this is just a projectile problem, so my motion is a parabolic trajectory. I initially go up, and then I come back down, and in this case I come down much farther than the height at which I emerged, and hopefully, assuming that you all do this problem correctly, there's a nice pool of water there for me to land in. Now, one of the things that we talk about when we talk about solving problems in projectile motion is breaking the problem up into phases. What are phases? How do I recognize when to use phases? The general idea of phases is that very often when you look at projectile problems, it's easy to break the problem up in such a way that you can solve for certain variables and then get to the end of the problem by simply multiplying. It's often easier than doing the full-blown algebra to get from one end of the problem to the other in one fell swoop. Often it's useful to break things up into phases so that you can answer questions about the problem. Maybe you were asked questions about the problem at intermittent points before the very ultimate end of the problem. So in this case, we could solve the problem beginning to end by simply applying the kinematic equations with just the initial conditions given here at the top of the ramp, given the initial speed and height and everything, and then computing what the ultimate result is. But I'm going to go ahead and solve this problem using phases to illustrate how we actually break the problem up. Both ways of doing the problem are perfectly valid, and as always in our class, it doesn't matter which way you solve it as long as you get to the answer that you're asked to find. So in this case, I'm going to divide this up into phases in the following fashion. I'm going to draw a dashed line straight across at the initial height of the ramp. Okay, and the reason I'm going to do that is because you can imagine that if I were to pretend that the top of the ramp were the ground, that this motion that I go through here is exactly the normal parabolic projectile motion that we've been talking about in class. And so as such, that means that all of the information about the initial motion here at the beginning is simply the same as the motion that it has here at the end, with the exception that the speed in the vertical direction is now negative. The initial angle is 40 degrees up here. The initial angle is 40 degrees down here. The initial x speed has some value here. It has the same x speed value over here. Okay? The motion, as we've discussed, is symmetric about the apex of the flight. Okay? And then similarly, if I look at the end of the problem here, I can imagine just solving this last little bit of the problem where the initial conditions that describe the plunge into the pool here at the end is defined by whatever the conditions are right there at that point where I return to the moment, the altitude I had when I initially left the ramp. So this is an example of the kind of diagram I would draw when I start recognizing phases in a problem. And so I would typically call this over here the motion from the time the problem starts to the apex, one phase. I would call this motion over here from the apex to the same height that I initially left a second phase. That's useful because this phase I almost never have to do any calculations for if I've solved everything in this part. And then last but not least, here at the end, I would usually call this phase 3. Okay? So we're going to use that as our setup here in order to solve this problem. As I said, there are more than one way to do it, but I'm doing it this way in order to illustrate this concept of phases. Okay, so no matter what I do, the very first thing that I'm going to need in any method that I solve the problem is I'm going to need to know what the components of the initial speed are. So let me go ahead and do that. The initial speed is some 14 meters per second like this. Okay. It has an x component. It has a y component, and those two are related through this angle of 40 degrees. So if I just do that trigonometry, I find that v naught x is equal to that initial speed, whatever it is, times the cosine of that 40 degrees. So that initial speed is 14 meters per second times the cosine of 40 degrees, and I find that that is 10.72 meters per second. V naught y is similarly v naught times the sine of 40 degrees, and that's 14 meters per second times the sine of 40 degrees, and if I work that out, I find that it is 9.00 meters per second. So those are the initial components of the speed at the moment that I leave the ramp, and as I said, I'll need that for any way that I go about solving the problem. Okay, so now let's do the first bit of the problem. I'm going to solve the kinematic equations to find out how long does it take me to get to the top here, and also how far it is that I travel. Okay, so I'm going to go ahead and do that. So I'm going to write out the kinematic table. This is a two-dimensional problem, so there are two kinematic tables, one for x motion and one for y motion. So I have x, x naught, vx, v naught x, ax, and t. And similarly over here, I have my y table, which is y, y naught, vy, v naught y, ay, and again t. Okay, so those are going to be my two kinematic tables. As with many, if not all, projectile problems, the time between the x and the y direction is the same. Okay, in this case it is unknown. The acceleration in the x direction is 0 meters per second per second. There is no acceleration in the x direction. So in particular, that means that the x initial speed is equal to the x final speed. That is, the x speed is constant. I calculated the x speed up here. It's 10.72 meters per second. The initial x position is 0 meters because I placed the origin of the at the location of the ramp, and so the final x position is unknown. Okay, so now I'll go to my y kinematic table. I haven't yet chosen a vertical coordinate here, but I'm going to do that now because I have to decide on some signs, and as is usually my habit, I'm going to define plus y to be up and y equals 0 to be at ground level. Okay, so if I do that, then filling out this kinematic table is now possible. So the acceleration in the y direction is the acceleration due to gravity. It points down in the negative y direction based on my coordinate choice I've made there. So I'm going to label this as minus 9.80 meters per second per second. My initial y speed I computed up here as 9 meters per second. It is upward, so it is a positive 9 meters per second for my initial y speed. What's my final y speed? Now in this case, we're solving this problem in phases, and in particular, the phase that we're working on is the initial phase of motion from the time that I'm launched to the time I reach the apex. And at the apex, I know something very special happens to the y speed, namely it goes to 0. Now I wasn't told that in the problem. That's one of those things that we have to recognize. Why not? Given where I chose my origin is the initial height of the ramp, which is 6 meters, and my final height is unknown. Okay, so those are my total kinematic equations. So in this case, the easiest way to get the time is from the kinematic equation for the y speed. So the kinematic equation for the y speed is Vy is equal to V naught y plus Ay times t. The reason that's a particularly useful equation is because some of that's going to go to 0. In particular, Vy is going to be 0 because by definition, I'm looking for that point where Vy goes to 0. So if I now solve this for the time, I see that the time is equal to minus V naught y over Ay. Okay, as we've seen before, I may feel a little bit of consternation about that minus sign, but that's okay because the acceleration, the way I've defined it here, is negative. And so when I divide a negative by another negative, I end up with a positive number, which is appropriate for a time. So let's go ahead and put the numbers in there then. So time in this case is equal to minus V naught y, which is 9.00 meters per second, divided by the acceleration, which is minus 9.80 meters per second per second. And if I multiply that all out, I find that the time is 0.92 seconds. So that's the amount of time it takes from the moment I leave the ramp to the time I reach the apex of the flight. Okay? Now, in particular, what that means is that it also is going to take 0.92 seconds for me to reach this point in the flight as well. Okay? So we'll come back to that. So now the next thing I need to do is, or that I want to do, is I want to find what is the altitude, what is the total height above the ground I am at the apex here. So I'll use the kinematic equation for y position here. So that is y is equal to y naught plus v naught yt plus a half ayt squared. So I know all of these things in this equation except for y there. So I can put those in. This is 6 meters is my initial y position. My initial y speed is 9.0 meters per second. My time, as we just computed, is 0.92 seconds, plus a half times minus 9.80 meters per second, times the time, which is 0.92 seconds, squared. Okay? And if I work all of that out, I find that the total height above the ground is 10.13 meters. Okay? So that is my final y height. And so I can now use that information to continue solving other bits of the problem. Okay? So let's go to a new piece of paper here. Now, ultimately, one of the things that I'm asked to find is the total x distance traveled. So if I'm doing this in phases, what I need to do is I then need to find the x direction, or the x distance traveled in each of the phases. So in this phase, I can get the x distance by simply using the kinematic equation for x, which is x is equal to x naught plus v naught xt plus a half ax t squared. Again, there's many things here that are zero, in particular the initial x position and the acceleration due to x. And so I'm left with a very simple equation for the distance. If I put in the numbers, my initial speed in the x direction, as we found, was 10.72 meters per second. If I multiply that by 0.92 seconds, I get that the x range just in this part 1 phase is 9.86 meters. Okay? Okay. So the whole point in working in phases is that the part 2 phase, which is the phase that goes from the apex down to the same height as the ramp, is identical. I've solved everything I need to know, or everything that I can know about the first phase, and so that means for phase 2, I know a whole bunch of information. Okay, in particular, I know that the final y is 6 meters because I started at 6 meters. I know that my final v is the same as my initial speed because it didn't accelerate or change, and we said that that was 10.72 meters per second. I know that my final y is identical in magnitude to my initial y, but is pointing in the negative direction. So in this case, it is minus 9.00 meters per second. I still know that ax is 0 meters per second. I know that ay is still the acceleration due to gravity, which is minus 9.80 meters per second. I know that the time it takes in phase 2 to go from apex down to this y position is exactly the time it took me to get up. And so the time for phase 2 alone, okay, is 0.92 seconds. Okay? And I know that my final x position is the distance in x I already traveled, plus that same distance again, or twice the 9.86 meters that we just talked about, and that is 9.72 meters. Okay? And then last but not least, I guess I knew this from my velocities up here, I know that the angle that I make with respect to the horizontal is the negative of the initial angle that I made. Okay, so I didn't have to do any calculation for phase 2, which is the beauty of carefully choosing your phases. Okay, so now the question is, what do I do for phase 3? Well, the whole point in phase 3 is that the initial conditions for that phase are simply the ending conditions in phase 2. And so I can make a kinematic table to solve the two-dimensional motion that will give me the last little bit of what goes on in this problem from the moment I pass downward through this horizontal layer, which is even with the top of the ramp, to the moment when I hit the pool. Okay? So, in this case, I think the easiest thing to do is to find my final speed Vy. That is going to be useful for finding other quantities. So the kinematic equation that I want to use in this case is Vy squared is equal to V naught y squared plus 2ay delta y. Okay? Now in this case, the value for the initial y is simply the final value for y at the end of phase 2. Okay? And delta y, which is y final minus y initial, this is y final minus y initial. Y final is going to be 0 meters because I'm going to end up at the ground. Y initial is going to be 6 meters because that is the place where I ended at phase 2. Okay, so if I put in all of those numbers, I see that Vy is equal to V naught y squared, so that is minus 9.0 meters per second squared plus 2 times the acceleration due to gravity, which is 9.8 meters per second, times delta y, which we found was minus 6.0 meters up here, all to the 1/2 power. Okay, and I've taken a square root here. Now, you know that when you take a square root, you have to make a sign choice as to whether or not the square root is positive or negative. In this case, we know that it has to be negative because my Vy is going to be downward. Okay, so I'm going to take that negative there. And so if I plug in all of those numbers, I find that the final y speed at the moment that I enter the pool is minus 14.1 meters per second. Okay? Now the reason I did that is because now solving time is easy from the equation for Vy. Okay, so the kinematic equation for Vy is Vy is equal to V naught y plus a times t. If I solve the algebra there, this is t is equal to Vy, that is V final y, minus V naught y all over ay. Okay, and if I plug in those numbers, Vy is minus 14.1 meters per second minus my V naught y. Well, my V naught y is minus 9 meters per second, so minus that is plus 9.0 meters per second, all divided by the acceleration in the y direction, which is minus 9.80 meters per second. If I plug in all of the numbers here, I find that I get that the time, just for that last little bit of the problem, is 0.52 seconds. Now, a word of caution here. That time is positive, as it should be. Okay, time should never come out negative. But getting this correct value for the time, and indeed getting that it is positive, is highly dependent on getting all of the signs correct throughout this entire problem. And so keeping track of signs and ensuring that you know what you mean when you say positive and negative direction when you're assigning values to things like acceleration and velocity are extremely important, or you'll get the wrong number right here. Okay? So last but not least, I need to know what my final x is, so I can use the x kinematic equation. The x kinematic equation is x is equal to x naught plus v naught xt, and I'll leave off the acceleration term here because we know in this case the acceleration in the x direction is 0. X naught in this case is simply the value for x that we started this phase. That's 19.7 meters. V naught x is the V naught that we had at the end of the last problem. That's 10.7 meters per second. And then the time here is the time elapsed in this phase, which is 0.52 seconds. That's 0.52 seconds. Okay, and so in the end, the final x distance is 25.3 meters. So that is the distance from the end of the ramp that we need to place the pool of water such that I hit the pool and don't die an unseemly death, all in the name of physics. Okay, so that's what the whole game is all about, and I'll talk to you again next time.